Hip hip, huzzah! Hip hip, huzzah! Welcome to our annual Night of the Stars spell. How amazing. I mean, we have been doing this, I think, for, I would guess, about 15 years.
Since 1833.
1833. Thank you, Don. That's right. But we've been celebrating this amazing night for about 15 years. But the reason why we celebrate this event, and we've invited the Denver Museum of Nature and Science, Dr. Lee and Dr. Koons to come and talk about the Night of the Stars spell and what is a comet and the Leonids shower, is that in 1833, on November 17th, at the time Bent's Fort was first constructed, there was the largest meteor shower that had ever been witnessed in North America. And there were over 100,000 meteors falling, I think every minute or something.
Probably per hour.
Or per hour, excuse me. But it turned night into day. And so there were all these accounts from the Indian tribes who were in their encampments. They would do hide paintings to the Mormons and to the small towns across America. And people thought it might be an omen, it might be the end of the world. And it was such a frightening thing at first, this whole cosmic experience. And at Bent's Fort, there was a Cheyenne encampment right outside of Bent's Fort. And when this event happened, it was like an omen. And was it a good omen or a bad omen? And everyone, you know, when I always see that, I always see like Owl Woman, who is singing the death song as the warriors mounted their steeds and rode around in single file around Bent's Fort, while the meteors are falling, trying to understand what is this. And so anyway, this night is, and this time of the Leonids shower is very important to us at the fort, because our fort is the first replica of Bent's old fort. And then we also wanted to bring Dr. Lee to describe what is a comet, what is, and also what are the latest things in science that are going on in the cosmos in general, and also Mars and NASA and all the exciting, and the cocktail comet. Dr. Lee, are you going to talk about the cocktail comet? It's spewing off sugar and alcohol or something?
I will make mention of it.
He'll mention it. And then we have Dr. Michele Koons, who is an anthropologist, head of the anthropology department at the Museum of Nature and Science, and she's going to be talking about the interpretation of the native, the hide paintings and the artifacts that they have there, and how it was interpreted with the native peoples. And I just want to say I'm really excited to have all of you here, and I will then start us off with Dr. Stephen Lee, who is a curator of planetary science and chairman of the Department of Space Sciences at the Denver Museum of Nature and Science, and is a research scientist at the Space Science Institute in Boulder. He's a science advisor to the Museum of Nature and Science, Space Odyssey exhibition, and frequently participated in the development and delivery of the museum programs, helping to bring the latest discoveries in planetary and space sciences to many of the 1.4 million visitors seen at the museum annually. He received a PhD in planetary geology from Cornell and has been at the DMNS since 2001 and SSI since 2006.
Actually, Michele is going first.
Well, then,
Sorry, I neglected
no, that's fine. I'm delighted. Well, Michele, you get to hear about her. She's amazing. She is a curator of archaeology at the Denver Museum of Nature and Science. She studies ancient complex societies and is especially interested in ancient political dynamics, social networks, and how people of the past interacted with their environment. In her research, Dr. Koons uses different geophysical methods and remote sensing tools, as well as traditional archaeological techniques like excavation and pedestrian survey. She has conducted archaeological research throughout the United States, Peru, Bolivia, Chile, and China. She is currently studying ancient irrigation systems management of the desert coast of Peru and co-directing a project in the Mongolian highlands of New Mexico, investigating the impact the changing environment has had on population dynamics through time. Dr. Koons has a BA from the University of Pittsburgh, MA from the University of Denver, and a PhD from Harvard. Let's give her a hearty welcome.
Thank you.
Let's say Harvard.
Okay. We dropped the H-bomb. I try not to do that, actually, very often. Well, it is just an honor to be here again to celebrate the anniversary of the Leonids event. And I'm going to give the same talk that in many ways that I've given over the last few years, but I've had some new things I've added into here. And so I hope you guys like it. All right, so people have always wondered about the cosmos. They've always been asking themselves, what are these things up in the sky? What are these celestial spheres that move from east to west? Why does the sun always rise in the east? Why does it always set in the west? Why are there sometimes stars that stay after the sun is in the sky, but then all the other stars disappear? Why are some stars different colors? And also, why do sometimes stars fall from the sky? And why does rarely a star appear and it stays for a while and then disappears, never to return again, seemingly? This has always puzzled people. People were always curious about this. And so we in anthropology have the study of archaeoastronomy, which is looking at past and ancient civilizations, how they understood the cosmos, how they understood it based on their written records, but also by studying the unwritten record, which could be architectural remains that are left behind or other features on the landscape. Anthropologists also study ethnoastronomy, which is the study of astronomy in more recent cultures that might not be looking at things from the same scientific perspective that we in our Western civilization have. And one really simple example of this is when we go outside at night, we see the man in the moon. That is the myth of our North American cosmology, more or less. We see the man in the moon. In South America, they see a rabbit. And if you look at the moon, you actually can see the rabbit pretty clearly, but it's just a different way of understanding the sky. So archaeoastronomy and ethnoastronomy are really important because they give us insights into these culturally embedded belief systems and ideologies that are different from what we think about today. And it really helps us to understand how people structured the world in the past. It's a way of really turning our scientific mirror on ourselves and cause for reflection and thinking about how we're looking at these things and how it may not have always been that way. And people today don't even think it's that way. So people in the past, they built many structures and features on the landscape that had significance for them understanding their cosmos, understanding the sky. And so, for example, the people in Chaco Canyon in New Mexico, a lot of these buildings in the canyon have significant solar and lunar alignments, which is really, really fantastic and interesting. Cultures like the Maya, they were renowned for their understanding of the cosmos, of astronomy. They were so good at understanding the sky that they were able to predict solar eclipses, they were able to predict certain planetary movements, and they have these incredibly complex calendar systems, both on that revolve around the solar cycle and also that revolve around the lunar cycle. So very, very complex. And you can think about this, it must have been a lot easier to watch the sky and to be in tune with the sky when you don't have the distractions of lights and TV and all of the modern conveniences, so to speak, that we have today.
Yeah, but they still got the end of the world wrong.
They didn't have it wrong because they didn't say it was the end of the world. We said it was the end of the world.
Sells books.
So I thought I'd talk a little bit about some of the interesting astronomical observatories in Peru. So as Holly said, I've spent most of my career working in South America, and this is a really fantastic site. It's Conchanquillo, and it's probably the earliest astronomical observatory in all of the Americas. It dates from about 350 to 100 BC, and the inhabitants there would have been able to accurately determine the date with an error of 1 or 2 days. It was that good. And how it worked was that there are these solar towers that you can see here that you would observe from a certain point on the landscape. And at one point at the winter solstice, the sun would rise behind the leftmost tower at Chanquillo, and then on the summer solstice, it would rise behind the rightmost tower, and this would these towers would then mark the passage of time. You had to stand at a specific place on the landscape. And this right here is what they call a fortress that is right there on the same site, and that was probably linked into this astronomical observatory. They call this the Norelco ruin because it looks like a razor, if you've ever seen a Norelco razor. So that is kind of
I thought that was a Spanish word.
So it's kind of silly, but you gotta like it.
Now I see the rabbit.
Exactly. So I also want to just talk a little bit about the Moche. I did my dissertation research on the Moche archaeological culture of the north coast of Peru. And if anyone wants to talk about this at some point, I'm game. I love it. But the Moche were awesome. They had these fantastic pyramid structures that we call huacas. They're made out of adobe. You can see right here. They're decorated with these crazy murals. They have this beautiful pottery that has these narrative scenes that it doesn't talk, but it has depictions of their gods and their beliefs in the everyday life. It's really, really neat stuff. So I did my dissertation research at this site right here called the Capados. It's a mid-sized ceremonial center which had these 2 really big pyramids, huacas, on it, and no one had ever worked there before. And so I was putting it on the map, so to speak. And my co-director for the project was really into archaeoastronomy. And so he was like, I think there's something going on here with the alignments of these pyramids. And sure enough, we noticed on March 20th, on the autumnal equinox, that the wall did not pass any shadow at high noon, at the northern wall of these structures. And he's like, yes, these are all aligned with the autumnal equinox. And so you can see here, this is the picture. I did my best. I had my clock watch out trying to take the picture at noon. And you can see here, this is the alignment of all of these buildings. It was 24 degrees east of north, and this particular site is about 7 degrees south of the equator. So fancy math that I don't really know everything about, but it was really, really exciting to have someone there who was able to help with this. And in fact, he has been working a lot with archaeoastronomy at other Moche sites, and one of the most famous Moche site is called the Huacas de Moche. It's located just outside of Trujillo, Peru, and it has the Huaca de la Luna and the Huaca del Sol. The Huaca del Sol is the largest man-made structure in all the Americas. It was 250 meters across by 50 meters high. The Spanish diverted the Moche River into it to get all the gold out. I don't know, who knows if they actually found anything, so it's much smaller now than it used to be. But he was able to show that there was a lot of significant stellar alignments at this site that marked the times of the Pleiades rising, which was really important for agricultural cycles, as well as other rising stars that we think were really tied into Moche ideology.
Are they mounds?
What's that?
When
They're
you say
adobe pyramids.
Adobe pyramids.
Yes, they're man-made structures. Yeah.
They're not basket filled mountains.
No, they're pyramids. Well, we call them huacas. They're temples, more or less. So in North America, we also see a lot of structures that are significant for observing astronomical phenomena. So, for example, the Bighorn Medicine Wheel, which is located in Bighorn Mountains of Wyoming. We see these medicine wheels all throughout the northern plains. They often have 28 spokes which is obviously a significant number in the lunar cycle. And this particular one was built in 1760, and it marks the rising of the Dawn Star and other events such as the rising of the Pleiades again, that marks drought seasons and agricultural seasons. And so pretty sophisticated way of ordering the world. So all of these celestial alignments that I've been talking about come from years and years of observation. These people were really in tune with what was going on. But comets and meteors were completely different. These are not predictable phenomenon, and they often threw people off. And as Holly was saying, they caused fear, they caused awe, it was confusion when something that was not supposed to be there showed up. And people were so in tune with it when it wasn't supposed to be there, it really did kind of throw things off. They oftentimes thought it was an omen for disasters or messages from the gods. In places in Europe, the people thought that the elongated comet looked like a fiery sword rushing through the sky, and which was a traditional sign of war and death. These messages from the gods, they could only really mean that the gods were going to wreak havoc and really bad things were going to happen. And so meteor showers were pretty similar. The fear of meteors was also a part of Aboriginal Australian oral history until at least the 1930s. We have some pretty interesting accounts. In 1921, this man named James Mitchell, he visited the Henbury Crater site with an Aboriginal guide. And Henbury Crater is in the Northern Territory of Australia. And he was trying to get close to this big crater that you can see there, and the guide would not go up there. He says that this is a place where the fire devil came from the sky and killed everybody. And so he was not able to get close, and he tried to go back again in 1934 with a different guide, and this other guide said no one would camp within 2 miles of this meteor site, and that no one would even venture within a half mile of it. He described this as the place where the fire devil lived. And so some anthropological work was done, and Aboriginal groups to the north of Henbury hold this tradition that meteors are fiery devils, they call them, but fiery devils, that would hurtle from the skies and feast upon the entrails of the recently deceased. So the craters in Henbury, what's really interesting, they were created 4,700 years ago. And so if these stories are actually, they might actually be oral histories that have been handed down for all those years. And we know that the Aboriginal Australians had really deep oral histories, but this is really exciting to think about this, and all revolving around meteors and what we're talking about today. Meteorites were also really curious to the Native Americans here, quite close to home. In Arizona, there's 2 12th century villages about 100 kilometers apart that both had these hidden compartments that once held chunks of meteorites that were, the meteorites were over 50,000 years old. And these meteorites, they came from the impact here of Meteor Crater, which is outside of Flagstaff. One of the sites was in Winona, and the other site was down here. And they both had these little compartments holding these fragments. And these fragments are not completely uncommon in this particular landscape, but the people must have been very fascinated by them. To think about it, these are iron, more or less, and metallurgy was not a part of their culture at this time, so they were probably fascinated by these particular objects. We don't really know what the shrines were for. So, the Leonids shower that we're here tonight to see, it occurs every November. And it's when the Earth passes through a meteorite stream of particles from the comet Tempel-Tuttle. And Steve is going to talk way more about the science of all of this. The Leonids is most intense every 33 years, more or less, or so. The last really big one we had was in 2001. And so we should be anticipating one in about 15 years, 16? Yeah, 15 plus. Who knows? We might still be doing this.
I'll put it in my book.
Yeah. Well, let's hope for a clear night, right? We had the earliest accounts of Leonids showers go back to 902 AD, which is awesome. There's Chinese accounts, Egyptian accounts, as well as, and it counts from where is now Italy. And there might be some even earlier. There's some earlier Chinese records, but we're not sure if it actually matches up to the Leonids or another meteor shower. But these accounts are actually of the Leonids in 902. So some other interesting times when the Leonids were recorded, 1630, and this is all before we really understood what was happening, so you can understand why it was still a little bit weird what was happening in the sky. So 1630 was, Kepler died November 15th, and then the brilliant Leonid shower was 2 days later. And so a lot of people thought that this was some kind of message from Kepler that, you know, they're like, oh, he's there, thanks.
They haven't started throwing rocks.
And then another time it was recorded in 1799 by Humboldt, a very famous scientist who worked a lot in South America, the Humboldt current, and he noticed it and recorded how incredible it was in 1799. And then this is a cool silk painting from 185 BC from China that was excavated and found in a tomb, and that actually has some meteors on it, but we don't know exactly when, if they're referring to the Leonids or something else. So the meteor shower that was produced in 1833 was by far it was brilliant. It was absolutely incredible. An estimation of 200,000 meteors per hour in North America is the number I have, which you can just imagine, just lit up the sky. And so a lot of these pictures here are from the Seventh-day Adventist Bible readings for the home circle. And you can see that, I mean, people were out in the streets, and they were like, what is going on? And I found this kind of neat story that was another oral history. We anthropologists like oral histories. That was from an ex-slave. Her name is Amanda Young, and she passed the story down through her family, and I found it from one of her relatives, and she said that from this night, I'm going to read it, somebody in the quarters started yelling in the middle of the night to come out and to look at the sky. We went outside and they were falling everywhere, big stars coming down real close to the ground, and just before they hit the ground, they would burn up. We were all scared. Some of the folks was screaming and some was praying. We all made so much noise, the white folk came out to see what was happening. They looked up and they got scared too. But then the white folks started calling all the slaves together, and for no reason they started telling some of the slaves who their mothers and fathers were and who they'd been sold to and where. The old folks were glad to hear where their people went. They made sure we all knew what happened. You see, they thought it was Judgment Day. Pretty powerful. All right, so the Lakota Sioux, as well as other northern Plains Indian tribes, they recorded this 1833 Leonid shower on their winter counts. I'm going to talk a bit now about what a winter count is. These are part of the pictorial calendars where each image represents a remarkable or unusual event that occurs within a single year. So they're part of this tradition of oral traditions as well as art traditions that contain some rock art that you see up in the northern Plains area. The winter count comes from the Lakota word. It's a Waniyetu Wawapi, and it means that which can be marked or read or counted. And what they are basically pictographs that are arranged in spirals or in rows, sometimes serpentine shapes, that were originally done on hides. The more recent ones are done on cloth and sometimes in paper. They were done with a bone brush, was dipped into mineral or vegetal paints. Later, outside influences brought in watercolors and crowns and other medium. The pictographs for each year often recorded some kind of unexpected or special event. So something that was chosen for a particular year, like a flood or a fire or the death of a leader or a really significant astronomical event. So each image represents 1 year, but it's counted from winter to winter, so that it kind of spans our Gregorian calendar. So some of the years seem as though they don't match up 100%. Oftentimes these span about 100 years. The earliest ones we see are in the early 1700s, and the latest one, they go until about 20s are some of the latest ones that we see. We don't know exactly how many there are out there right now in the world. It's thought to be in the dozens. It's really not that many that have survived. There are 8 winter counts at the Smithsonian Museum. We have 1 at the Denver Museum of Nature and Science. The British Museum has 1, and there are a few in South Dakota in the Sioux Indian Museum, and I'm not sure exactly on how many they have there. And in general, we just don't know how many are in existence. The winter count keeper was the person who was responsible for recording and remembering the events each year. And he would use this calendar to tell these stories and kind of keep that oral history and the tradition of the people. The people would oftentimes, they would tie themselves into those winter counts. So like, I was born in the year that the stars fell, or I was born in this, and so this happened in that particular year. So it was really a good way of remembering and keeping track and order to the world. The winter count keeper would consult the tribal elders, and they would choose which event was the most significant for that year. The job, as well as the narrative, was handed down from male apprentices, usually from father to son or from father to nephew, and the apprentices would then copy the original document and keep it going. So there's oftentimes many documents that record some of the same events that were happening because it just kept going. Sometimes these original documents were buried with the winter count keeper when he died. Other times they would survive. So there's different fragments of them. And it seems as though everyone that we know about all depict the 1833-1834 meteor shower, since it was the most memorable thing that happened that year. Oftentimes these winter counts that we know about, they don't have similarities except for the night that the stars fell. And so this is really the Rosetta Stone that links them all together, and so that we can actually understand what was happening in these different Lakota and different bands that we can then start to bring the pieces of the picture together. You can see these are some of them from the Smithsonian winter counts. So this is the White Horse winter count that we have at the Denver Museum of Nature and Science. See it pretty well here. This records the history of the Lakota Sioux from the Cheyenne River Reservation in South Dakota, and it spans the years of 1789 to 1915. It was kept by Chief Whitehorse, and it's double-sided. I'll show you the other side in a little bit. Whitehorse had no male relatives, so when he died, it was kept by family members, and then it was purchased by a collector and eventually donated to the museum in 1983. This is Martin Whitehorse right there in 1868. So until only a few years ago, the whole story of the winter count at DM&S was unknown. We knew it was a spiral winter count starting right there in the middle with the crow moving around, but we didn't really know what else was being told from these pictographs. We knew that the night that the stars fell was on this piece, but that's pretty much all we knew about it. But as it turns out, this winter count was transcribed on September 8th, 1910, and the history was told by Chief Whitehorse to Florence Thwing, who was on the Cheyenne River Indian Reservation in Timberlake, South Dakota. See, Florence's husband was Whitehorse's attorney, so they had really close ties with the Lakota people, and she was the one who sat down and really took notes on every single year and what that meant. So the transcription was kept by Florence, and then it was inherited by her daughter, but it was not known about until just about 6 years ago, when her great-granddaughter, Libby Holden, was going through a trunk of old things in Minnesota, and she discovered this typed 32-page document. So Libby said that her grandma never ever spoke of this document, but they decided to send a copy to Whitehorse, South Dakota, and the town was just rejoiced when they found it. They were like, wow, this is the history of the people in the town. This was just absolutely incredible. And the connection between this document and the DM&S winter count was made by Jim Nelson of the Timberlake Area Historical Society. And so he was trying to figure out more about this transcription that he had. He, just right before this book called The Year the Stars Fell was published and it's about all the Smithsonian winter counts. So he was looking through this to try and just learn more about the winter count and what he could figure out. And he saw a reference in there to the Denver Museum winter count and thought, heck, maybe this might be the one. And so he called and confirmed that it was an exact match. And so this transcription, discovered 6 years ago, matched up with the Denver Museum of Nature and Science winter count that was donated in 1983. Pretty awesome. So the winter count is remarkable. I mean, it provides the history of the Lakota people through their eyes, what they thought was important, what they thought was the most significant thing that happened each year. And we now know what corresponds to each pictograph. So right here, this one, the first one, is the year that many crows were frozen to death. This is called the year of the death of the crows. In 1910, here's the backside of that one. This one's done on muslin. This, another astronomical event, this was the year we saw a great comet in the sky. It was called by the white people Halley's Comet.
Oh, so that
See
makes
there?
that, yeah.
Okay, and then we see this right here. These ones I find very fascinating. 1803, the year we got smallpox. And then 1820, the year we got smallpox again, more or less. And the thing that's interesting about these is I was looking at a lot of the winter counts, and there's a lot of smallpox. And they're in different years, so they're not between the different bands. And so they're not Rosetta Stones like the night the stars fell, which you see right here, 1833. In the year of the stars moving around in the sky. So, all right, when I was looking over my notes to come back and give this lecture again, I was trying to, think of if I could find anything new and exciting, and I was like, you know what, I haven't really looked to see if we have any other winter counts in our collection. I highly doubted it because there's only, like I said, in the dozens. But I was like, I want to see what's in there. And to my surprise, I found out that we actually have 2 replica winter counts that were done in the 1960s by a Sioux man named Herman Red Elk. And I was just very curious about these. And so I pulled both of them out, and I pulled out their files to see what I could learn. So the first of these 2 is a spiral winter count, starting in the center and moving around. And the records are confusing. And they say, I'm going to read, the original, made by High Hawk, belonged to Baptiste Good, father of High Hawk and Joe Good. It was done with berry juice and later traced with crayon. It was a notebook and was pawned to a storekeeper for $5. He sold it to R. Brusus of Valentine, Nebraska, who gave it to the Sioux Indian Museum. It had no translation and was water soaked, so the pictures ran together. Our copy was done by Herman Red Elk. So the first problem with this is that the style of the pictures on this winter count does not match those on Baptiste Good's winter count at the Smithsonian. And we know that High Hawk was Baptiste Good's son and continued the Baptiste Good winter count. Since the winter counts record each band history, we would expect that the DM&S winter count was a copy, if it was a copy of one made by High Hawk, made by Baptiste Good, that the pictures should match up, but they don't. You can see here, this is one, for example, this particular year, completely different. So I was confused. So then I looked at the other winter count the other replica winter count from 1960, 7927, really clunky name, which the records say was a copy of Big Missouri's winter count, which was copied by Kills 2. And this is a linear winter count, like that. And it contained, in the DM&S records, a full transcription of each image, which is pretty cool. But I quickly realized that the 26 and the 27 were actually the exact same icons. And they were just in a different format, one being spiral and one being a linear. And they both referred to the Big Missouri Kills 2 winter count, of the which is in the Sioux Indian Museum in South Dakota. So I have some research to do because I'm really confused as to why that record was in our record saying that it had something to do with the High Hawk Baptiste Good. And I'm going to make some phone calls. Maybe next year I'll be able to figure out if we have something in our collection that relates to a different winter count. It's never a dull moment. But the thing that's really cool about this winter count was when I started looking at it, this is the same winter count that's in the famous picture by Kills 2. And you can look, and it's like all the exact same images. Right here is the night that the stars fell, 1833. And you can see right here, they use the exact same symbol, the cross symbol that they used on the White Horse winter count to mark the winter of the falling stars. So, yeah, like I said, a lot more work to do. But winter counts are, like all historic and archaeological counts of astronomical activity, they really give us a better understanding of the way the people who made them were thinking and what they thought was important and how they were ordering their world. And so today we have a science that Steve is going to talk about to really explain how things work, but traditional knowledge and myths and religion, they're all really important, and they're really important to understanding our past, understanding the past of, well, all human past. And so Jesus is just one example of that. So thank you. I brought both the Big Missouri and the White Horse transcriptions, if anyone wanted to see them, and also the book. So.
Well, thank you, Michelle. And it's really amazing to think that this type of thing has been going on for thousands of years, really. And the way I like to think of it is ever since people were people, they were out around their campfires before we invented artificial lights, and they were very, very familiar with the night sky because that's what you had to look at for essentially half the day. And when something like the Leonids happened, it really set people on their heels because this was something that was very unusual. It wasn't predicted. It wasn't this regular thing of the moon and the sun and the planets moving through the skies. So it really became an amazing event. But just cutting to the chase of what meteors are, we know that now that they are related to debris coming off of comets. And for the Leonids themselves, this is the comet that is their origin. It's called Comet Tempel-Tuttle. And it goes out into the very far outer solar system, comes back in, and in the course of doing this, it sheds dust and sand that are what caused the meteors. So this is sort of the schematic of this. We have this debris cloud following the orbit of the comet, and then periodically the Earth slams into that debris cloud. And all of those little pieces of dust and sand and maybe pebbles burn up in the Earth's atmosphere. Relative to the Earth, they're moving probably 10 to 20 miles per second, and when they hit the atmosphere, they just vaporize. Very seldom does one of them actually survive to hit the ground, and that's meteorites that we find on the ground. But most of these meteor showers, it's just an atmospheric phenomenon where the debris burns up in the Earth's atmosphere. And this is just an example for the Leonids. Back in 2006, we have all these clumps of debris coming off of this comet. And here was day by day how the Earth would track through some of those debris clouds. And next year, it might come into this, so you'd have a few more meteors happening on particular dates. Every 33 years, we end up coming through much more massive clumps, and that's when we see a lot more meteors. Typically, on the Leonids, you might get a few dozen per hour if you're lucky, and then, like in the 1833, it's not a meteor shower, it's a meteor storm, where you have tens of thousands to hundreds of thousands of meteors per hour burning up in the atmosphere. And it's really hard to tell or to predict exactly ahead of time, but we can say roughly every 33 years we get into these denser clumps. And sometimes they're much denser, like in 1833. And so that's where we get these really amazing events. This was taken in 2001 from an Earth orbiting satellite looking down on the Earth, and you see these were the Leonids coming in from above. So let's sort of set the scene here about what are comets. And this is just a sort of a graphic of a comet. First of all, we have, we believe, a nucleus, which is the actual physical part of the comet. It's a dirty ice ball or an icy dirt ball, however you want to characterize this. And it's typically only less than 10 kilometers across. And that we can't see from the Earth. We can't resolve something that small. But what we do see is the cloud of gas and dust that surrounds the comet. That could be maybe many tens of thousands of kilometers across. That we can see. That's right up here. And then, of course, we have these very dramatic tails streaming away from the, caught up in the solar wind, streaming away from the sun. Those could be several tens of millions of kilometers or miles across. And let me give a little bit better view of this here. So up at the head of the comet, we've got the nucleus buried in there somewhere. And then as it approaches the sun, the gas and dust from the nucleus is driven off, and that forms the coma, this big cloud around the nucleus itself, and then it gets entrained in the solar wind. And if the sun is over here, as the comet orbits the sun, the tail is always away from the sun. And so, and then we also have this, what's called an ion tail, and that's the magnetic field and the charged particles from the sun that basically light up this gas. It's like a neon light tube. And so that's the blue part of this, and that can also be very spectacular.
Steve, you should mention to the folks with that slide the direction the comet is moving.
The comet itself is probably moving like this around the sun.
The other way.
And
It's the other way, isn't it? The ion tail is always first, and the dust tail is always second. The dust tail trails behind the ion tail.
okay, you're right. You're right. But the sun is basically over
Right.
in this
it's
direction.
moving downward in this
It's
picture.
always,
Okay.
always is away.
That's right. Thank you, Ed. Keep me honest here. So, what we really know about comets now have really come about in the last roughly 30 years. And that's since we have the capability to send spacecraft past the nuclei of the comets and really get up close and personal with these ice balls. And so the first one of these was in 1986, and that was what was called the Giotto mission. It was a European mission, and it went past the nucleus of perhaps the most famous comet of all comets, which is Comet Halley. And not really great results from this mission, other than they got within a few thousand kilometers of the nucleus, and they actually were able to see the nucleus. So this is the ice ball that leads to Halley's Comet, and then there's all this stuff being driven off of the comet itself. The next really big mission, a really successful mission, was the NASA Stardust mission, and that flew past Comet Wild 2 in 2004, and what really distinguishes this mission is it had this sample return capability. And so this is about the size of a tennis racket. It, as the spacecraft flew through the nucleus, or I'm sorry, through the coma of the comet, this tennis paddle was stuck up into the debris cloud, and the spacecraft itself was traveling through it at something like 15 miles per second. And so any of the dust that hit this this sample collector stuck to it, and then that was folded up and put into this sample return canister. And this is what the nucleus of Vilt-2 looked like. It's roughly sort of like a hockey puck shape when you see it from all sides, and that was actually the best view of a comet nucleus we'd had to that point.
How big is that?
It's about 5 kilometers in the long dimension, and it's just a couple kilometers thick. If you were to rotate this, it would be much thinner in the other direction.
Is Halley's the same size?
Halley's is about, I think it's closer to 12 kilometers in long dimension, so it's actually much larger. So, in January 15th of 2006, the Stardust spacecraft returned to the Earth. It dropped off the sample canister, the sample return vehicle, and it landed in Utah. This was the re-entry of that. It made a very nice meteor of its own, in its own right. And here's the canister when they flew up to it in a helicopter and picked it up. And then they brought it back. It was opened up in the same lab that all the lunar samples are contained in Houston at Johnson Space Center. So there's the sample device. And when you look at that, each of these little sort of ice cube sized rectangles are filled with what's called aerogel. It's essentially solid smoke, is what some people have called it. It's sort of silica. It's quartz that's 99.9% vacuum in it. And when things hit it, there's one of these impact sites. And when you look at it from the side, so this is the front of this aerogel, and it slows down the little dust particles that are slamming into it. And all these little black things right at the end of these streaks, those are the comet dust. And they've got several hundred of these samples on this this tennis racket, and they're over time analyzing all of these. And this is our first sample of a comet itself. So the next big mission was Deep Impact, and that went to Comet Tempel 1 back on July 4th of 2005. And this was the first time we'd actually tried to reach out and interact with a nucleus. And we did that by dropping off an impactor. And let me quickly show you a little cartoon of how that happened. And so this is the mothership. The impactor approached the nucleus, and it slammed into it at something approaching 20 kilometers per second. And then the mothership diverted itself so it could watch the fireworks. And so here's the impactor slams into the nucleus itself and creates a crater. And then as the mothership passes by, it can observe the fireworks. So that's the way it was supposed to happen, and in fact it really did. So here's the nucleus. This is only about 3 kilometers, I think, in the long dimension. Here's where the impactor hit. And here we go from the mothership watching the impact happening. So that actually worked, and they learned a whole lot about the structure of the comet by seeing how this happened. And so now we're in the current era, and there's actually a spacecraft that has been orbiting Comet, I'm going to mess this up, it's 67P Churyumov Gerasimenko.
Gesundheit.
57P it is much easier. And so this is a European Space Agency mission. It arrived in August of last year, and around a year ago, I think it was November 12th of last year, it dropped off the Philae lander, which actually set down on the nucleus of 67P CG. And so as they were approaching the nucleus, this was when it was still a few months out, and you can see that it sort of looks like it's irregular. It's certainly not a spherical object. And once they got even closer, this is what it looked like, and it's sort of it's called a contact binary. They think there's two pieces of this, and they probably hit each other and stuck. A little more whimsical, it's a rubber ducky. And so once they actually got in orbit around this comet nucleus, this is what it looks like. And you can see that there's really two pieces to it. It's about 5 kilometers or so in the long dimension, and pretty amazing object. And so I'm going to spend much of the rest of the talk just leading you through what we've found out in the last year. First of all, this, to put it in comparison, this is an artist view of it next to Mount Fuji. So it's something, we can sort of wrap our arms around almost. It's big, but it's not that big. And so this was back a year ago, the landing attempt from Philae. So Philae itself is about the size of a dishwasher.
Washing machine.
So a washing machine, something like that. And so the mothership is, the Rosetta itself stays in orbit around the comet, and then they dropped off Philae. And the idea was it would land on the nucleus. The intent was that it would stick there. It has 3 legs, and they had ice screws in the legs, and they would quickly burrow into the surface. There was a thruster, a little rocket on top that would hold it down while that was happening. And then there were little harpoons that were supposed to be fired into the nucleus. And the reason it needed all of this is the comet is so small that this several hundred kilogram mass lander on the Earth only weighs about as much as a piece of paper on the comet. Or it has that force holding it down. And so they were afraid that it would bounce if it wasn't held down. Unfortunately, all 3 of those systems failed. And so indeed it bounced. And it bounced actually 3 times before it came to rest. So this was how it was supposed to work. It was supposed to be attached to the nucleus. It had this little robot arm that would go out and drill. It had other instruments that would look down. It had cameras that would be taking panoramic images. Not so much. So here's where it was intended to land. And in fact, it bounced. It came down and hit the rim of this crater wall, and then it came down on the other side, and in fact it almost just bounced off into space, but it didn't quite. Here's the view as it was coming in for its first bounce. This was taken just a few minutes from the surface, and so very high resolution. This boulder sitting there is probably half the size of this table. And here's when it finally came to rest. They think it's next to a sort of a cliff wall. Unfortunately, it's solar powered. It was in this sort of shadowed area. It only, instead of getting sunlight for many hours a day. It was getting it for a few minutes a day.
Oh, no.
And so it wasn't able to charge its batteries, and so there was about 60 hours of battery available that was charged up when it before it separated from the mothership. And after about a little less than 60 hours, it went offline. But they did get a lot of information back. They claim about 80% of the intended science has been returned.
Oh.
They hoped that when the comet got nearer the sun, that it would, the increased energy coming in from the sun would be enough to wake up Philae. And so this was in November of last year, and in fact in June, they heard from the lander again.
Oh.
Unfortunately, it just kept coming up for a few minutes, and then it would fall away for a few weeks, and then it would come up again, and they haven't heard anything from it since I guess it's mid-July. They're still hopeful. But in fact, they don't even quite know where it is. They think that this is an area about the length of a football field. Somewhere in there is where the Philae lander is sitting. But they have to be in exactly the right geometry with the orbiter to be able to communicate with it. And they're hoping to be able to do that again in about a year. So just quickly, I want to give you a tour of 67 CG. So it's these two lobes. There's this neck in the middle, and it's just an amazingly complicated place. Lots of very steep walls, and remember, this is not rock. This is ice, and it's very volatile. As it got closer to the sun, I'll show you some images in just a second. It's spewing stuff out at a tremendous rate. So here's the neck again between the two sides of the comet. If you're into mountain climbing, I expect you'd have a lot of fun, except every time you hit it with your axe, if the axe didn't stick, you'd go floating away into space.
What's the surface temperature?
It's about, at best, about minus 100 centigrade. So whatever that is, 200 and some degrees below zero Fahrenheit.
What is absolute cold?
Minus 273 would be absolute zero.
Yeah.
They think that the interior of it is much colder than that, but it's an ice cube.
What took those pictures?
Pardon me?
What took those?
The Rosetta spacecraft. So the orbiter is taking these.
It's still active?
It's still active, and they expect it to survive until about September of next year. So the comet itself, and I should have thrown in a picture of this, but it orbits from about Jupiter down to sort of midway between the Earth and Mars. And most of the time it's sort of in a deep freeze. When it gets closer to the sun, like it did sort of starting in February, March of this year, and its closest approach was in August of this year, that's when the comet turns on, so to speak. It gets warm enough that the gases and ices start evaporating and they get driven off of the surface, and that's what makes it look like a comet.
How long does it take to make an orbit?
Oh gosh, it's
Earth time.
It's about 6 or 7 years.
So Philae still has a chance.
Philae still has a chance.
Does it rotate itself like the Earth rotates?
It does, but it's rotating about once every 5 hours. So it's spinning pretty rapidly.
As it rotates, doesn't the lander get into the sun? Yeah,
So that was the idea, that potentially, as it gets closer to the sun and the sun gets brighter, instead of only being in the sun for a few minutes a day, it might be an hour a day or so. And they think that's actually what happened, but the geometry between the orbiter and the lander is such that they could only hear it at particular times, and they needed to be fairly close. And I'll show you in a minute why they had to back off. So these are just sort of close-up views of these boulders, and remember, these boulders are actually ice, not rock, and they look like they're falling apart. There's rubble piles around the boulders, and that's exactly what you'd expect. It's got dust and sand and material mixed in with the ices, but then as the ice evaporates, it just sort of falls apart, sort of like a charcoal briquette.
Sloughs off,
left that side. Pardon me?
It just sloughs off.
Right.
Yeah.
Okay, so here's more recent images now. You see all the gas boiling off of this comet.
When you say boiling, it got a little.
Well,
come to the point that it's probably 175 degrees below zero.
Right.
Instead of 200.
It's warm enough that it's evaporating, and as it evaporates or sublimates, then it gets driven off of the object itself. And here's a really spectacular series here. These were taken over the course of about 10 minutes, so here you don't have much happening. Here you got this jet or geyser going off, and it lasted for maybe 10 minutes, and then turned off again. And this was on the day of the closest approach to the sun. You can see it's really active, which is what we were hoping to see. This is just a sort of a time lapse showing this boulder being ejected from the comet itself. And they can't really place a size on this. They say it's between maybe 1 and 50 meters. So, you know, the size of that podium to half a football field. So somewhere in there. But this is the type of stuff that the meteor showers are derived from.
Right.
So you get all this stuff driven off of these comet nuclei. They're still in orbit around the sun, and if you have this debris cloud, then every now and then the Earth runs into those, and that's where the meteor showers come from.
Excuse me.
Yes?
How long will it take a nucleus that size to completely evaporate?
That's a really good question. So how long can these things last? Potentially millions of years. But what more than anything does them in is, as they're traveling through the solar system, every now and then they might get close to Jupiter, get close to Mars, get close to the Earth. That alters the orbit, and it makes it so that they get closer. Some of them fall into the sun.
Yeah,
They get close enough that they just go poof. Others, all the ices are driven off, and then they become asteroids, we think. They're dead comets, but all the dusty stuff is left behind, and then there isn't the gas to break it up. Yes?
Where did the ice come from originally?
That's a good question.
In the beginning.
Where did these come from? So, right, in the beginning, we think that as the sun is forming, or a star is forming, you get these big clouds of gas and dust that start collapsing in toward the center. And as the star itself ignites, and you get nuclear fusion going on, then in the outer parts of that solar system, in quotes, it gets cold enough that the gases start condensing into ices. And so we think that the nuclei themselves form way far out, well beyond Pluto, so tens of times farther away from the sun as what Pluto is. And then eventually either there's collisions or there's another star passes somewhere nearby that perturbs the orbits, and they start falling in toward the star. and that's where the comets come from.
So when you call it ice, could it be just frozen hydrogen or frozen gas? Of some
Well,
other sort?
and Holly had asked me to talk a little bit about this, but it's not just water. There's carbon dioxide, there's methane, there's ammonia, there's cyanide, there's all sorts of stuff that's driven off of these things and that form them. And then you've got silicates. You've got the stuff that the dust and the little pebbles are made out of. And you've got organic compounds that
I said it's amino
make
acids.
things. So, right, so there's lots of junk involved in these things. Yes,
When the debris drops off, the comet's still in its orbit.
right.
What keeps the debris fixed in what was the orbit?
Well, it's not fixed, but it's following the same path around the sun as what the comet was. And that's just gravity, basically. But the small dust grains, the small particles, they can actually get blown around by the solar wind and by the pressure of the sunlight on them. And so eventually it starts spreading around. So it's not just a nice orderly procession. It starts sort of getting more chaotic. And that's why you see those things like there's a cloud here, a cloud there, and it, eventually dissipates.
About 9 months ago, there was a comet that they had a period on it, and they had seen it pass behind the sun.
Right.
And then the prediction was, this time, it's not coming back. And the prediction was correct. It went behind the sun and
it never came out the other side.
So it probably just either evaporated or it was pulled down into the corona.
Right. So what I wanted to show you here is this is a view from Rosetta as it got close to the nucleus. It actually got within about 7 or 8 kilometers back early in the year. And what happened is there's all this dust and pebbles and things coming off of the comet. And in order to stabilize the spacecraft, they look at stars. They have what's called star trackers, and that's how they say, here's where we're pointed, and they stabilize themselves. The star trackers started seeing
nuts.
all this stuff, and they lost stability on the spacecraft, and it started spinning. And when that happens, it does what's called a safe mode, where it just sort of pulls in its arms and legs and says, "Help me!" and so it's in this orbit where they sort of come in close, and then they move out away from the comet. And so in that safe mode, it waits for the Earth to tell it what to do. And so they said, move away, basically. This stuff is dangerous.
Yeah.
And so at that point, they raised the orbit so that it was typically 100 to 1,000 kilometers away from the nucleus, and that's what they've been doing since. And that's one reason why they haven't been attempting to talk to Philae anymore, is because they're not close enough to do it. But the closest point to the sun was back in August, and now they're moving out again. And so the activity of the comet is reducing with time. And probably within the next few months, they're going to be able to move closer to the nucleus again. And then next September, when they're ending the mission, they want to do another attempt to get really close. And in fact, they're going to set the Rosetta spacecraft down on the comet itself. And they expect that'll be the end of the mission, that they won't be able to communicate because they won't be able to point the antennas. But they're hoping when that happens, they'll be close enough, that'll happen very slowly, that they'll be able to regain communication with Philae.
Wow.
And so this is the most recent image that has been released. It was taken 3 days ago.
Oh, wow.
And so there's a little bit of activity still happening, but not nearly what we were seeing back in August.
The thing too is with the low gravity that thing has, the slightest little perturbation in the surface where you have those jets, it's constantly changing its orbit as it goes.
It is. So it's like little rockets going off that change it. So
What is the process by which the metaphor, as a comet dies, it metamorphoses into
an asteroid, is there cementation? Is that, how does it, what
No,
happens?
I mean, imagine, again, I call this sort of a dirty ice ball.
Right?
And once you've driven off most of the ice, that the ice is evaporated, then you're left with the dirt that's left behind. And at that point, it's not active anymore. And so it's just the stuff that's left.
The stuff that's left solidifies.
Well, it doesn't solidify. It's just that you don't have the gas being driven off anymore, and so it's much more stable.
Yeah.
It's not. I mean, it might have the consistency of talcum powder,
Yeah.
but you don't have the gas disrupting it. And
It's
so
jillions of particles flying in close proximity.
well, I wouldn't necessarily say that.
Well, you're
They're-
talking
but they're-
talking about right here.
It's sort of, again, like a charcoal briquette, if you will, that it's sort of powdery stuff, but there's enough gravity that's holding all the powder together that it stays there. And that really is different than asteroids, which are probably, most of them are rock and whatnot, but for all intents and purposes, we can't tell the difference. And so that probably a lot of these asteroids that are coming past the Earth are failed comets. Or dead
Unless they're
comets.
not.
Unless they're not.
So
So
it's time we're in big trouble.
I need to tie this off, I guess, because we're all hungry. And so just getting back to the Leonids, the best time to see these are going to be Wednesday night, Thursday morning of this week. And the usual mantra is go out a few hours after midnight, sometime between midnight and dawn is the best time to see them. Look off in the east. This year we've got Jupiter off in the east, which is going to be a very bright star, and so that'll help you find Leo. But most of the meteors, as they come streaking in, are going to be near the tail of Leo. And the good thing this year is there's a crescent moon. It sets at about 10 or 11 p.m. our time. And so if you go out at midnight or so, it should be a fairly dark sky. And this is just a time lapse that I found on the web of last year's Leonids. And so there's Jupiter, or I'm sorry, that's not Jupiter because I wouldn't have been there last year, but this is Leo, and that's what it may look like. And so just if you're out and seeing this, just imagine that we're not civilized people, that we're people 5,000 years ago watching this, and how amazing this could be for us. So, thank you.